All right. So today we're going to continue this ongoing discussion about random walks. Uh, we're going to focus on undirected graphs. I guess that's the same as last time. Last time was undirected graphs. Um, well, let's put it this way. The first lecture was about directed graphs and talking about actually eigenvectors of the random walk matrix being related to a stationary distribution. Last time was about undirected graphs and this connection between a linear system solved by the hitting times uh, and vertex potentials of electrical flow to get sort of this kind of indirect analysis. And so today we'll sort of combine elements from both. We're going to look at undirected graphs, but then we're going to look at the eigenvectors of the random walk matrix and things like that. And we're going to be able to say more than we could about directed graphs. Okay, so along the way, hopefully expose you to some nice mathematics. All right, we're off to an auspicious start. Um, right, so we did this, we did that. So today is this. Okay, so recall. Right, so we already know that in any directed graph, there's always a stationary distribution. And if the graph is strongly connected, it's even unique. Okay, and that turned out to be a matter of just understanding the linear algebraic properties of the random walk matrix. Right, the combinatorics sort of disappeared. And so today, we're going to prove something even stronger than just the existence of a stationary distribution. The question is, say you're walking around doing a random walk, how long does it take to converge to a stationary distribution? How long does it take to converge to a stationary distribution? And we are going to do this analysis based on the eigenvalues of the random walk matrix. Okay, so we already know from Perron-Frobenius, from directed graphs, the maximum eigenvalue is 1. Okay. Today we're going to show that all the eigenvalues are real. That's not automatic. And they're the eigenvalues are at most 1 in absolute value, so they're between 1 and -1. So if I ordered the eigenvalues mu1, mu2 down to mu n in decreasing order, okay, and again, all the other eigenvalues have absolute value at most 1, but suppose there's a gap, okay, so suppose I let gamma be the maximum of mu2 or negative mu n basically, okay, so I'm hoping there's some separation from -1. Like if all the eigenvalues are between 1/2 and -1, except for the one corresponding to the stationary distribution. Okay. Then, if I take k steps of a random walk, and I measure the difference in L2 norm, right? So maybe initially I start at one vector, so all my probability mass is 1 at this one vector, and you take a random step, now it's like 1/2 here, 1/2 there. You take another random step, 1/4, 1/4, 1/4, 1/4 or something, right? So over time it's diffusing as you're taking a random walk. And that I always have a vector corresponding to my distribution, some vector summing to 1. And I look at the L2 difference, so sum of squared difference, was the stationary distribution after k steps. Okay? And it's going to converge to something related to the maximum and minimum degree. That's sort of a... but the important thing is 1 minus gamma to the k. Okay, so if there's a constant gap, like 1/2, all the eigenvalues are between 1/2 and -1, it's going to converge exponentially fast to a stationary distribution. Okay? And conversely, if gamma is really small, you're not guaranteed as fast of a rate. Okay? And so you should think of, something like a line graph, n vertices long, right? It's going to take a long time to get to the other side. So at the very least, n steps to get to the other side, to even just get non-zero probability on the other side, right? So in that kind of situation, you should expect gamma to be really, really small, because it can't converge that fast, because it just takes a long time to get to one side of the graph or the other. Maybe it's more compelling if you thought about the cycle, because stationary distribution will be equal everywhere. It sort of has to be by symmetry. And so if I start here at the top of the cycle and I look at the vertex on the exact opposite, it's going to take at least n over 2 steps to get to the other side of the cycle. And I'm only at the stationary if the whole thing is 1 over n everywhere, right? So that tells you that some graphs are going to take longer than others. So, we're kind of going now back and forth. You look at the graph, you can extract some eigenvalues, right? Tells you something about the random walk, but you can also look at certain graphs and be like, oh, the random walk's going to take a while on this. That's telling you something about the eigenvalues, right? So there's some kind of interesting thing going on. And in general, we're learning how to analyze graphs with a different set of tools than, say what I typically teach in undergrad algorithms or something. Oh, that'll be the maximum degree and the minimum degree over all vertices. And if it's weighted, it'll be weighted degrees. Okay. So that's at most square root n. Okay, yeah. Yes. Yes, yes. So yeah, so you're either the difference between 1 and mu2 or the difference between -1 and mu n, if it's listed in that order. Yeah. Okay, so good. So to do this, we just need to understand something about symmetric maps. So, okay. The main example we're going to be working with, a good working example because it also lets you bring some combinatorial intuition at the same time, is modeling undirected graphs. Okay, so we're going to take an undirected graph and represent it by a symmetric matrix called the Laplacian that we introduced, I think, last class, right? We talked a little bit the Laplacian, so I'll reintroduce it. So first, I'm going to introduce it this way this time, a little bit differently. So, what sometimes people call like XY transpose. So you kind of make a square matrix out of it where the 1, entry is X1, Y1, the N entry is Xn, Yn. Okay, that's called a rank 1 matrix. It's really just 2 vectors. Okay. And so the terminology I'll use is this outer product terminology. And one functional definition is the outer product, as a matrix, you always have this. Okay. For all X and Y. Okay. And Y, right. So it's this kind of thing. Okay. So, okay, why do I mention this? We're going to model each edge as a rank 1 term. Okay. Where the vector, it's one vector with itself. That vector puts a 1 at U and a -1 at V if it's an edge between U and V. It's an undirected edge, so you could have switched 1 and -1, but it doesn't matter when you take the outer product with itself. So although assigning 1 or -1 might seem arbitrary, it doesn't matter for defining the edge. Okay. So what this is going to do is if I take any vector x, which is kind of assigning values to all the vertices, right, and I plug in my rank 1 term for the edge, it's going to take the sum of differences squared and return that value, right? So this is some edge, and you're going to get this value xu minus xv squared for that edge. Okay, so I'll define that as, I guess, the Laplacian of a single edge. And the Laplacian of a graph will just be summing all these up. Okay, so if it's a weighted graph, I'll do a weighted sum. Okay. So it's a sum of m rank 1 terms, one rank 1 term for every edge. Okay, so if I look at what happens when you evaluate a vector x, what are you going to get? You're going to get something that looks like this. Okay, you're going to be summing up over all the edges. What's the difference between the endpoint squared times the weight of the edge? Okay, so that's the graph Laplacian. Nothing else down here. Okay, so I think we did this last time, but I'll do it again just to remind us. So the graph Laplacian, maybe it looks technical, but it's a little bit intuitive. For example, it does encode all cuts. Oh, no, that's the wrong slide. That's the next slide. I want to mention this though, that this matrix is symmetric. Okay? It's symmetric because each of those rank 1 terms, LE, which is the outer product of a vector with itself, the same vector, that's symmetric. The transpose would just flip the two vectors and you get the same thing. Okay? And you can see from the sum of squares definition that XAX is always equal to 0. In general, whenever you take a vector and outer product with itself, you'll get something where XAX is always greater than or equal to 0. Right? This is a matter of, so if you did something like, if you're looking at the outer product of y with itself and you're plugging in x, then our definition says this is xy squared. This is always greater than or equal to 0. Okay. So at some level, so this is just two things to point out. When these two things happen, it's called a positive semi-definite matrix. Okay. If this was strictly greater than 0, it would be called positive definite. Okay. That doesn't really come up much in this class. Okay, so like a week ago or something, we talked about eigenvalues and eigenvectors and how every linear map has an eigenvalue and an eigenvector, and we did some trick proof. Okay. We are going to strengthen that claim. So we're going to look specifically at positive semi-definite matrices. That's this nice class of matrices. And we're going to strengthen it in two ways. First, we're going to argue there's always a real eigenvalue. Okay. And not only that, but I'll give you like an optimization problem to solve it. Take your symmetric matrix L, which could be the graph Laplacian, and try to maximize XLX over all unit vectors X. Okay. The claim is that the maximizing vector X, there always is one because the space of unit vectors is compact, is going to be an eigenvector, and the value it attains, XLX, will be the corresponding eigenvalue. Okay. So two things coming out of this. One, X was over real vectors of unit length. Okay. Which, if L was also real valued, means that mu is real valued. Okay, so that's great because at some level, complex values are kind of useless for us, right? So like knowing that there's complex eigenvalues, eigenvectors, like what are you going to do with that? I don't know. But if they're real, okay, now we can do something. So this is, again, much stronger than general matrices. So somewhere it's based on this positive semi-definiteness. But all right. So, okay. So we're going to try to prove it. Okay, so let's try to prove it. So I guess we're going to say, let X, I'm going to fix X in this proof to actually maximize this inner product over L. Okay. And the first claim is that for any vector U is orthogonal to X if and only if it's orthogonal to Lx. Okay. That actually implies that X and Lx have to go in the same direction. But we'll come back to that. So how do we prove this? Any ideas? Actually, what's this? Oh, let's go through this first. Sorry. If the claim is true, let me just say what I said out loud. Okay, that means that Lx has to be spanned by X. Okay, because it's orthogonal to everything orthogonal to X. So there's some mu1. Okay. But not only that, But because since x is unit length, uh, so the existence of mu1 is one thing, but the other thing is that mu1, which is mu1 xx, and now I plug in mu1 x for lx, you'll get xlx. Okay, so if we can just prove this claim, we'll be done. Okay, so now to prove this claim, what could we do? I know someone was about to raise their hand, but maybe change their mind. Okay. So x is maximizing xlx over unit vectors x. And we want to argue that any vector orthogonal to x is orthogonal to Lx. Yeah. Oh, that's okay. Good. I think that's actually better than what we have. So, oh, no, you have to be a little bit careful actually. So let's look at this. Suppose I went from x to x plus epsilon u. Okay. Now, actually, this might be okay as a short proof. So the unit length, that means you went from unit length 1 to, so when u is orthogonal to x, right, then you just have like a Pythagorean theorem kind of thing. So the length is going to go to x squared plus epsilon squared u squared. We can take u to be unit length without loss of generality. So this is going to 1 plus epsilon squared. So you've increased this a little bit, right? Now, on the other hand, when you go from, okay, so if you look at this, this is like xlx, which we had before, plus 2 epsilon u, sorry, ulx plus epsilon squared ulu. Okay, just expanding things out. Now, what do I want to point out? So you can also write xlx divided by norm of x over all any x or something, right? Norm of x squared. So the denominator is increasing like 1 plus epsilon squared. There's an epsilon squared term. It's quadratic. So when epsilon's really small, it's growing quadratically. Now here, if ulx is anything non-zero, you can assume it's positive, right? The numerator is growing linearly. Okay, so just make epsilon really, really small. So epsilon squared is way, way smaller than epsilon ulx. So if I increase a little bit, right, from epsilon 0 to the actual epsilon, then you're getting about LUX points per increase in epsilon. But your denominator is increasing by at a much slower rate, right? Because epsilon is much smaller than XLU. So yeah, if you're looking at this numerator, I mean, if you're looking at this whole, okay. So the numerator is growing linearly in epsilon, and the denominator is growing quadratically in epsilon. Some constant times epsilon or epsilon squared. So for really tiny epsilon, arbitrarily small epsilon, the numerator is growing much faster than the denominator. So the value will go up. Are we okay with it? Because I have more calculations where we actually write down the thing and look at the derivative, but it's going to be the same thing. Yeah. So this fraction is the original problem is let x maximize xlx over norm of x equals 1. And I could have written that as maximize over xx over any x not equal to 0. Right? So setting the norm of x to be 1 is just normalizing it. Yeah. So suppose ux is 0. I want to show that ulx must be 0. So suppose it wasn't. Okay. Now let's look at what happens here when I take my original xlx and I change x to x plus epsilon u for a very small value of u. Okay. This shouldn't go up if x is the maximum. Okay. But now the numerator, it grows like xlx plus 2 epsilon ulx. Right? So it's some constant times epsilon. So numerator grows like 1 plus epsilon. And the denominator, because x and u are orthogonal, if you look at x plus u, the length squared, you get x squared plus epsilon squared u squared. Right? The xu inner product disappears because it's 0. So the denominator is growing like 1 plus epsilon squared for small epsilon. So numerator is growing like 1 plus epsilon. Denominator is growing like 1 plus epsilon squared. Okay. So numerator is growing faster than denominator. So it'll go up a little bit at the beginning, which can't happen if x is maximum. Yeah. There should be like 20. And there's 20 more in my office with typos. Yeah. It looks like there's plenty over there in that group, maybe. How many people? Uh, oh, we have, okay. So I'll print out like 25 next time. Okay. Yeah, if does anyone want more? There's more copies of the lecture. Oh, well, if people sitting next to each other want to be kind, that's okay. Or I can give up mine, and then if I panic, I might need to steal it back. Uh, no? You'll take one? You don't deserve it. You came late. Okay. Good. So, so that's the argument. If you wanted to, if you have felt too hand wavy, you could, write this out actually as a function of epsilon, and you'll come to the same conclusion. So, hey, this is supposed to, oh, it's down here. Okay. Uh, knowing that x maximizes xlx, that means that 0 maximizes f of x. That tells you a derivative of this function as 0 must be 0. And if you write out that gradient, you'll come to the same conclusion. Okay, but it's the exact same argument as before. It's really what happening is that one term is quadratic and one term is linear. Linear wins in the short run. Okay, good. Good, I'm glad, because that part would have been boring. All right, good. I'm happy. I'm so happy. I'm easily. Okay, so we have those things down, and wait, we've already done the proof, right? So I don't know what's left. Yeah, we've done this. Okay. Okay, so that completes the proof. Okay. Yeah. Because x has unit length. And then since Lx is equal to mu1, that's how I plug in at the end. So things work out really nicely for positive semi-definite matrices. For an arbitrary matrix, it's not going to come out nice like this. XLX for arbitrary L is not particularly meaningful. Okay. Good. Good. All right. So we've shown that there's one real eigenvalue, one real eigenvector. Okay. We even have some approach to obtain it. All right. The next claim is if as long as L is symmetric, okay, you actually get n real eigenvalues, n real eigenvectors, and they're all orthogonal to each other. Okay. And then, and that you can write L as the sum of n rank 1 terms. Lambda 1 times V1 outer product V1 plus lambda 2 times V2 outer product V2, so on and so forth, lambda n times Vn outer product Vn. Okay, that's insane. You start off with like these n squared arbitrary numbers, and you've kind of turned it into n principal directions, right? Those directions are all orthogonal to each other. So if I'm looking at a vector x and I want to know what it does, right? I can say, oh, well, what does it do with respect to Vn, with respect to do with V1, right? So x is going to multiply itself with V1 and shoot off that far in the V1 direction. It's going to multiply itself with V2, shoot off that far in the V2 direction. So symmetric matrices have these principal axes, right? It's really like a lot of symmetry. It's very strong. Okay, and we'll see why it's useful when we come back to random walks, either at the end of this class or the next. So good. Okay, how could we prove this? What's the first step? Get rid of orthonormal? Oh, so sorry, your first step of the proof is to just reduce the statement and do something easier. Ah, okay, orthogonal. So, okay, maybe you've seen this before. Okay, well, okay. I was hoping someone would say step one, we apply the lemma we just did to get at least one eigenvalue and one eigenvector. That seems like an okay first step, right? Okay. So, uh, we're going to actually try to prove this by induction on n, the number of dimensions. What's the base case? Yeah, but what's even easier than n equals 1? Okay. N equals 0? It's very easy. Okay. All right, n is at least 1. And as the first step, yeah, it's a 0 by 0 matrix. What's the issue? Yeah, are you upset about the empty set? Like, if you run out of money in your bank account, are you going to go to the bank and say, oh, this is not well defined? Okay, so at the first step, you might extract one of the eigenvalues, one of the eigenvectors, right? Okay, and I'm trying to set up stage a proof by induction. How can I turn this into an n minus 1 dimensional problem? I know there's multiple ways to prove this. We're committed to this path. Yeah. Yeah, so how do I, from L, I guess, all components of that from, what's X? Okay, so I kind of want to extract, I want to remove, so we're doing it on dimension, and so maybe I can try to like remove the direction captured by Vn. Okay, so yeah, so what we're going to do is we're going to look at this matrix B, okay, where the mu1 is unfortunate, isn't it? Oh no, we're okay. That's exciting. Okay, so I've kind of extracted this component, which if you kind of know what the theorem is supposed to say, then it really means we're subtracting the component. Okay. Now, if I want to do induction on B, though, I can't just do induction on B right away. What's missing from the hypothesis? What? Yeah, so I need to find a subspace that's n minus one dimensional where it's really going from one to the other. So let's look at the subspace orthogonal to Vn, which I just wrote arbitrary stuff here. Oh, it's getting crazy. Okay. Vn comma y. So I'm looking at the orthogonal subspace to Vn, and the claim is that B is maps y to y. Okay. So now B is a symmetric map inside uh, this subspace, okay, and we can recurse. Yeah. Okay, so if I look at the set of all vectors orthogonal to Vn, it's like, oh, I have the x, y, z axis, but I want to be orthogonal to the x-axis. What's left? The y and z axis. So that gets me into minus one dimensional vector. And then we can do induction on B and Y. That'll give us the n minus one vectors, which are all in the Y space, so they must be orthogonal to Vn, and they're all orthogonal to each other by induction will be done. Okay. So we need to show that B maps the orthogonal subspace to the orthogonal subspace, right? So that sorry. Yeah, so that means something like Vn By equals 0 for all y and y, right? Okay, so let's do this. Vn By, and then what? Sorry? We'll expand B, Vn A minus mu n, Vn outer product Vn uh, y, right? Okay. So let me maybe break that out. Vn Ay minus mu n Vn En outer product Vn y. Okay. Now what? Okay. So this is 0, like we want. Okay. Now we just have to deal with the other one. We can transpose A. A is symmetric. So A transposes A. Okay. Now what? It's the eigenvector equals 0. Okay. So B is mapping this subspace of n minus 1 dimension back into itself. It's still symmetric. It's still positive definite. It's symmetric because A minus V outer product V transpose will just get you A minus V outer product V. And you just do induction by on B, you're done. All right. So that's that. Good. Good. Okay. So I guess this is the point we made earlier, but I want to point out that this is like very, very nice. Like this idea that I can take this arbitrary array of n by n numbers, right? And I can break it down to these n principal directions. So let's look at the effect of such a matrix L on X if V1 to Vn are the eigenvalues. So V1 to Vn is an orthonormal basis, right? So I can take X and write it uniquely as some combination of these vectors, right? And so that's just changing coordinates, right? So I just write it in the coordinates of these vectors. And, if you expand out L, right, you'll get something like this, okay? And, okay, so, which is, something like lambda 1, V1x, V1, lambda n, Vnx, Vn, okay? And now if I plug in for x, the representation of x in these coordinates, it's orthonormal. So V1 inner product V1 is 1, but V1 inner product V2 is 0, V3 is 0, V4 is 0. So this is just alpha 1, right? And so on for all of the coordinates. Something like this, right? So it's very simple. So alpha is the coordinates in the V1 to Vn basis, right? So another way to say this is the following. Every positive semi-definite matrix is a diagonal matrix, right? Under an unknown rotation, right? You just don't know the basis, but there's some basis for which it's a diagonal matrix. So if you could just take X and you write it in that basis, then all that's left is what you would do with a diagonal matrix. But diagonal matrices are like the easiest things in the world, right? There's nothing like linear algebraic about it. All of your intuition from regular math carries over diagonal matrices because it's just n dimensions. They're completely separated from each other, right? So every positive semi-definite matrix is secretly a diagonal matrix. It might take some effort to find the rotation, but for analysis, yeah. Yeah. So imagine, so V1 to Vn are orthonormal vectors in some space. So if you can rotate the space, then they become your principal axes, just one coordinate at a time. So I could take X, I can write it in these coordinates, whatever X is, right? And if I look at what Lx is doing, it's saying, oh, in the first coordinate, it's your coordinate alpha 1 stretched out by lambda 1. It's like lambda 1 is in the top left for you guys. Yeah, top left of the matrix. And then there would be alpha 2, lambda 2. Lambda 2 would be in this 2 by 2 slot of the diagonal matrix, right? So basically there's a rotation, a diagonal, and a rotation for any symmetric matrix. The rotation is described by the orthonormal basis. Yeah, that's right. Obviously, it's not hard to figure out the eigenvalues of a diagonal matrix, right? So everything's easy with a diagonal matrix. Positive semi-definite matrices are diagonal. Everything is easy with positive semi-definite matrices. Actually, this is symmetric matrices in general. Positive just means the eigenvalues would be non-negative. So that's tremendous, right? If only life were that easy. Okay, any questions? Yeah. Yeah, so from B, you start outputting n minus 1 eigenvalues and eigenvectors. And the eigenvectors are in Y. They're already orthogonal with each other by induction, and they're orthogonal to Vn because they're in Y. Awesome. Okay, so uh, now we'll go back to random walks, and hopefully this will give another demonstration of the value of these symmetric matrices. Okay, so again, we know that directed graphs have stationary distributions. All right, so here's a claim. For any undirected graph, letting R be the stationary distribution, be a random walk, then the stationary distribution that's proportional to the degrees. The vector that's proportional to the degrees. So take all the vertex degrees and scale it so that it sums to 1. Okay, that's a stationary distribution. The graph is connected, then it's unique. Okay. So a stationary distribution, look at an undirected graph, you wonder what's the stationary distribution? It's actually quite easy. It's just proportional to the degrees, no matter how weirdly structured the graph is. Okay, a lopsided graph, a click here and a long tail, same thing. Always be proportional to degrees, right? Another unbelievable thing. Okay, so how do we prove this? No, R, so yeah, that's a good point. So R is not, R is not in the unweighted graph, or it can be the weight of edges. Yeah. Yeah, you actually just have to check it, right? So, okay, so one thing is you can write S the stationary distribution, okay? If you look at the adjacency matrix applied to the all ones vector, okay, and you divide by the total sum, which is W. No, it's 2W. Okay, you'll get the degrees divided by the sum of degrees. Okay. So the random walk matrix, so let's say that I'll let D be the vector of degrees, and D be the diagonal matrix of degrees. Okay. So R in this terminology is AD minus 1. Okay. And S is D over 1's D. Yeah. Yeah. But W is just scaling things to sum to 1. It's the only distribution proportional to degrees. And now we just plug in R is equal to A D minus 1 D over 1's D, which is A1's over 1's D, which is D over the sum of D's. That's your stationary distribution S. Okay, so you just plug in and check. Okay, nothing exciting, nothing really to do with spectral theorem yet. Good. Good. So now let's do the stronger things. Now that we know exactly what the stationary distribution is, let's try to figure out how to argue that we converge to it. I guess we probably won't finish. Well, we could if we wanted. Okay. Maybe we will. Okay. Oh, okay. No, we have some more work to do. Okay, fine. But we are closer than you'd think. So, all right, let me just lay a little bit more groundwork to save some time for next time. Okay. So I want to apply this symmetric thingamajig that we did. Um, but the random walk matrix is not symmetric, right? That's the basic issue. So we're going to massage a little bit based on something called similarity. Okay. So two matrices A and B are similar if I can kind of map one to the other with an invertible matrix C, right? So if C is invertible, that means it really preserves all the linear algebraic structure, right? You have some isomorphism. So you can think of like C, when I say C minus 1 BC, applied to some vector X. So Cx is going to take X and map it into, warp it into this other space. You apply B and you warp it back. And that whole thing is A. Okay? And you could, so if A and B are similar up to this, isomorphic warping, then they're similar. Okay. So I guess we can probably do one claim. Lemma. C gives an isomorphism between the kernel of A and the kernel of B. Okay. I mean, it's just saying it's a bijection. So if I only apply C to the kernel of A, the kernel of A is a subspace. Then it's claiming first it's going to map things into the kernel of B. Okay. And not only that, but the mapping is invertible. So this is just breaking some things down. So we can just verify this. So if X is in the kernel of A, right? First we need to check that if I apply B to C of X, that should be the zero vector, right? So here, BC is equal to CA X, which is equal to 0. Okay. And I guess the other one is you have some Y in kernel B. And now you're going to look at A C minus 1 of Y. And you want to show that this is 0. Right. C minus 1B of Y, so that's 0. Okay, so no big deal. Okay. Okay. So now the claim, then, this will be our last claim. There's not even a proof, it's just a Y. So the claim is that A and B have the same eigenvalues and C maps eigenvectors of A to eigenvectors of B. Ah, that's right. So that means if this is true, then that means you always have A minus lambda I is equal to C minus 1 B minus lambda I for all C for all lambda, since of course C minus 1 lambda I C, I doesn't really matter, right? And you just get lambda I. Okay. So two similar matrices are going to have the same eigenvectors and things like that. They are going to, just be kind of warped from one space or another via C. Okay. So, I'll only say that, what we'll look at next time is we'll take the random walk matrix and we'll look at a similar matrix where I apply d to the minus 1/2 on the left and d to the 1/2 on the right. Okay? And that'll give me a symmetric matrix called the normalized random walk matrix. It's symmetric. We can start applying that powerful theorem we worked hard to prove. Okay? And we start learning a lot about the random walk via the similar normalized random walk matrix. And it's going to tell us everything we need to know. So we'll do that at the beginning of class next time. All right, thank you. All right, so let me remind us what we did last time. We started talking about trying to get a better analysis for undirected random walks. Again, this is coming off of a few lectures in a row about random walks, from directed random walks in PageRank to this really cool connectivity and login space by random walks. And so today, and last time, we're looking at undirected graphs in particular. Okay, so you already know a stationary distribution exists. You know the random walk matrix has some nice properties just from the Perron-Frobenius theorem. As we're going to see, or as we already started to discuss, it has even nicer properties. And so this is the goal of today. We should be able to get there pretty soon. I want to show that if gamma is the difference between 1, which is always the maximum eigenvalue, and the absolute value of any other eigenvalue, okay, then, and I start at any distribution x, I will converge to the stationary distribution in L2 norm at a rate of 1 minus gamma to the k. So in particular, if gamma is a constant, you only need like log n steps or something. Okay, so this is like, a convergence bound, which we hadn't really had. So it's pretty strong. And if you guys remember, this is really turned out to largely be about graphs and stuff. So we're talking about symmetric graphs and positive definite matrices and things like this. Laplacian is one such example. And whereas we previously showed that every matrix has some eigenvector, we showed that if L is symmetric, like a Laplacian, then there's actually more direct ways to get eigenvectors, eigenvalues, and moreover, you're promised that they're real. They're real valued. So maximizing this inner product, XLX, this inner product over L, subject to all unit vectors X, that will actually just give you an eigenvector and an eigenvalue. In fact, it will be the biggest eigenvalue. And this was our proof last time. All you do is kind of perturb it while maintaining unit length and look at the first order optimality conditions. And so once you know that there's always one real valued eigenvector, that leads to this more powerful spectral theorem, which says that that for any symmetric matrix, okay, over n dimensions, I can get an orthonormal basis v1 to vn and real valued coefficients lambda 1 to lambda n. Okay, that L is the outer product of all these orthonormal vectors, weighted by the lambdas. Okay. So I'll just remind you, the proof is not so bad. We just use this lemma for one eigenvector to pull one eigenvector out, and then you do induction in the orthogonal subspace. Okay, so you just peel out one dimension and induction, you're done. Okay, so the peel, I think part of the goal of this lecture is to just really appreciate how powerful this decomposition is. So, so V1 to Vn, if it's an orthonormal basis, it's some kind of coordinate system, rotated coordinate system. And if you take any vector x, you write it in this coordinate vector system, unique combination of VIs, and you apply it to L, then you get something really simple. It says, okay, for x, alpha 1 is the coordinate in the V1 direction. Stretch that coordinate by lambda 1. And I guess I didn't write alpha 2, but alpha 2 would be the same. Look at the coordinate in the V2 direction. Stretch it out by lambda 2. And all the way through. So you just end secret principal axes, and you're just stretching, or flip it if it's a negative sign, I'll flip over, in that direction, right? And what it's really saying is that every symmetric matrix is a diagonal matrix up to some rotation. V1 to Vn, that's a different orthonormal basis. So instead of your choice of XYZ, it's some other XYZ. Okay? So you just have to tilt your head, and it's a diagonal matrix. Right? And diagonal matrices are trivial. There's nothing complicated about them. Right? You add them, multiply, they even commute. Right? AB is equal to BA. That's not true of matrices in general. In fact, half of the issue if you're doing operator theory is that even if you have two symmetric matrices A and B, because they have different eigenvectors. AB is not equal to BA. So if you're in this space of operator theory, trace inequalities, whatever, basically this is like 100% of your issues. And you're just trying to get around the fact that AB is not equal to BA in general. But with diagonal matrices, there is equal, life is very easy. Okay, good. So this brings us to random walks. I think this is roughly where we got to. I think we did a little bit more as this handwriting attests. So one is first to quickly point out that in undirected graph, you actually know the stationary distribution. It's always proportional to the degrees. And all we did was verify it. You just plug it in. The eigenvalue is 1. That's what it means to be a stationary distribution. So that's very nice, right? That's not true in general. So you don't have to do any complicated computations to figure out the stationary distribution. That's it. Okay. All right. So this is the theorem we want to work up to. Okay, we discussed a little bit similar matrices. Okay, so just to set the stage, I want to take all this nice stuff about symmetric matrices and apply it to the random walk matrix. But the random walk matrix, even for an undirected graph, is not a symmetric matrix. Okay, but we're going to show that it's almost symmetric in the sense that we'll show it's similar to a symmetric matrix. Two matrices are similar. A and B are similar if they're sort of like separated by an invertible map. So A is equal to C minus 1 BC. So C is invertible, so it preserves all structures. It just warps you into a different space. So you go from A space, you kind of warp into B space, do the mapping there, warp back, you get A. Okay, so they're structurally very similar. And I think we concluded with the observation that if A and B are similar, then they're going to have the same eigenvalues, and then C is going to give you a mapping of eigenvectors. So, and the easiest way to see this is just that, A minus lambda I is equal to C minus 1 B minus lambda I. So, like, just by, what are the values of lambda that makes this not invertible? And C preserves kernels and that was it. Okay, so two similar matrices, same eigenvalues, and eigenvectors map over in a natural way via C. That's the key thing. Good. So, now we're caught up. All right, so that brings us to this. So again, R is the random walk matrix, which is A D inverse, which is the diagonal matrix of the degrees along the diagonal, because you're at a place and you're going to choose one of your edges uniformly at random. So you divide by the degree and you add that much along each edge. Okay, so if I apply D minus 1/2 to the left and D 1/2 to the R, square root of D. So D to the 1/2 means I take the square root every entry. Okay, then this normalized random walk matrix Q is symmetric. If you expand out R is equal to AD minus 1, then the D to the 1/2 will cancel out and you get D minus 1/2 AD minus 1/2. Okay, so this is a symmetric matrix, and it's also similar to the random walk matrix. So I'm just applying D 1/2 on both sides. Okay, so all the eigenvalues should be preserved, and moreover, okay, so good news, Q is symmetric. That's great. Q has the same eigenvalues as R. That's also great. And so that means that Q must have this form, right? So Q is symmetric, so there's some orthonormal basis V1 to Vn, and eigenvalues mu1 to mu(n) here listed in decreasing order. And I pointed out that the first eigenvalue, the biggest one, is going to be 1, but why? Why should the first eigenvalue of Q be 1, the biggest one? Of R and? Okay, so it's going to have the same eigenvalues as R, and then we have the Perron-Frobenius theorem from R land, right? So we know that the biggest eigenvalue is always 1, and everything else has absolute value less than equal to 1. Okay, so we can apply Q. So we have two things going on. We have the symmetric theorem being applied to Q. We have Perron-Frobenius theorem applied to R, and they're connected because they're similar matrices. Undirected graphs. Okay. So yeah, maybe this is a good question. So where in this are we leveraging the fact the graph is undirected? And that's because then A is symmetric, which lets you conclude that Q is symmetric. That's the only point, as far as I can tell, where the undirectedness plays in. Okay, good. All right, so Q has this decomposition. This is just the same as last time. And so that tells you, right? Uh, so d to the 1/2 should be mapping eigenvectors over, right? And we know the first eigenvector corresponds to the stationary distribution for R. Okay, so just applying this mapping d minus 1/2, it tells you that d 1/2 v1 should be proportional to the stationary distribution. Okay, and we know the stationary distribution is proportional to the degrees, okay, up to scaling. So, and then knowing that v1 is supposed to have unit Euclidean length, right? So in other words, if I want to figure out exactly what v1, the first eigenvector of the normalized random walk matrix is, I know that d to the 1/2 v1 is equal to alpha times d for some d, right? And it's going to be scaled to have unit Euclidean length. So we can do d to the minus 1/2 applied to both sides, and then normalize it. And you get v1. So that gets you, I hope I wrote it. Okay, good. So, right, so v1 is going to be the square root of the degrees divided by the Euclidean norm of this, yeah. Just the degrees as a vector, and big D puts it along the diagonal. And just working that out, I mean, you get square root D dot product square root D, that's just the sum of degrees. Yeah. The eigenvector for the biggest eigenvalue. Yeah. Because we know that the stationary distribution is sort of the first eigenvector of R, and now you have this similarity mapping. Yeah, so if you just kind of plug in, Q v1 is equal to v1 into up there, and you also know that Rs is equal to S, where S is a stationary distribution, then that's what you get. Okay, so clearly, like we're learning a lot about these random walks or undirected graphs, which we wouldn't know in general. Okay, so spectral decomposition is just giving us everything for free. No algorithms are needed. So I guess this is just plugging this back in. It always has something of this form. All right, good. Okay, good. Making some progress. Yeah, so element-wise square root of the degrees. Yeah, just kind of making up some notation as we go along, but hopefully it's clear what it's supposed to mean. Oh, the rain has passed, so that's good. Okay, so with that in tow, we are going to try to prove this thing. R to the k minus s less than equal to 1 minus gamma to the k, where gamma is a spectral gap. Okay. All right, let's see what happens. Okay, I left this blank. Hopefully there's a reason. Okay, so um, uh, let's look at r to the k x. Okay, uh, that's what we ultimately want to analyze. But what I want to do is kind of think in terms of q, because q like really has this nice structure. So how can I try to inject q into this? Yeah. Yeah, yeah. So I think that's what we have. Okay, so here I'm just plugging in for R, hopefully correctly. And now what happens when you expand it out? The inner terms cancel out, right? So you get something like this. Okay, so this is very, well, we'll see. But, R to the K is very similar to Q to the K. I guess basically, literally in the sense that we're similar as well, but like, yeah. Okay, so did I write the next one ahead of time? No. Okay, so now let's expand this out, right? So this is like d to the 1/2 times, okay, this is going to be painful to write out. So let me use some tricks. Okay, uh, this to the k, d to the minus 1/2 x. Okay, all right. And now what? Yeah, this is. I mean, yeah. So what if Q was a diagonal matrix? It's really a rotated diagonal matrix. Each of the entries would just go up to the kth power, right? So if I took a diagonal matrix in high power, does the same thing happen here? Yeah. So whenever you have like these terms, if you have like V2 and V3 like this, and this should work out to like V2 dot product V3, V2 outer product V3. Okay. And what do we know about the V's? They're orthonormal. So all those cross terms go to 0. So it really is just like a diagonal matrix. So as I take, just take k squared. K is 2, I mean, right? Then you're going to have all these cross terms from the different VIs. And whenever you have different VIs, it just vanishes. So you're just going to end up squaring the eigenvalues and the same vectors will still be there. So good. So let's see. Maybe I could have made this bigger. Okay, so when I take this to the kth power, then what's going to happen is I can move this, and this will go to the k, and this will go to the k, and things like this. Okay, the first one there's a 1 there, and 1 to the k is 1. So uh, this is very nice, right? Now, okay, so our goal is to show that this thing goes to the something like the stationary distribution, right? So where does the stationary distribution appear in this? Yeah, or more specifically, there's a lot of D's. Yeah, so let's look at this term. There's a comma missing there. Okay. So, all right. Oh, sorry. What does this kind of thing look like? Uh, okay, let me do this a little differently. We'll eventually get to this point. But like, what does this? Okay, well, let me just put it back. Okay, right. You're going to get uh, D will be from the first one, outer product all ones over the ones D vector. Okay, and if there was an X here and there was an X here, this will give you D. Sorry, this will give you ones comma X D over this. Okay, so the outer product rule is like, okay, if I have a matrix, outer product matrix, this matrix just gets applied to the first vector. That matrix gets applied to the second vector. If you want to think about U, V transpose, that'll work out too. Okay. And so you'll get the outer product ones divided by the sum of degrees times X. And then you'll get one dot product X degree over sum of degrees, right? Okay. How can I simplify this? So this is an X. I know it comes out kind of scrawny. How can I simplify this term? Sorry? Yeah, so the stationary distribution is this d over 1 over d. So I need to get rid of 1x. How do I get rid of it? What is x? X was my initial distribution of my random walk. So x sum to 1. And this is just summing up x. So you get the stationary distribution. Okay? So, okay, so what does that mean? That means you have something like uh, rk to the x minus the stationary distribution, whereas the stationary distribution is proportional to the degrees, right, is equal to all of these remaining terms. Something like this. Okay. Um, okay, let me just make sure I don't take us off the well-beaten path. Yeah, we're doing okay. Okay, so, okay, good, good. So are we still with me at this point? That's a little mathy. Okay, so I'm going to call this, I called it S in the notes, but S is already taken. What letter should we use? W taken? Okay. So W, not to be confused, is like weights of edges or something. Okay. So, okay, if I look at the norm squared, norm squared, and so this looks like, um, yeah, uh, D to the 1/2, W, D to the minus 1/2, X. uh, d to the 1/2 w d to the minus 1/2 x, right? Okay. And so this will look like, I'm going to move 1d over by taking the transpose. Okay. So I just moved the d to the 1/2 over. It's diagonals, it's symmetric, things like this. Okay. Now I got to deal with this term. I want to kind of remove this d. So the claim is that this is less than equal to, and I'll let you fill in the blank, some blank wd minus 1/2 x wd minus 1/2 x. Ah, okay, this starts looking like our eigenvalue eigenvectors, right? So, so remember we did like xlx. So this is x, this is L, this is x. So this will be at most the largest eigenvalue of D, okay? Where D is a diagonal matrix of degrees. So what's the largest eigenvalue of D? Yeah, the largest entry in D, which is the maximum degree in the graph. Okay, so eigenvalues of diagonal matrices aren't so bad. So this is delta max, okay? And now, let's do this. Or let me do another one. So I'm going to write this as delta max. I'm going to move a w over. D minus 1/2 x uh, w squared. W is symmetric. Everything here is symmetric. D minus 1/2 x. Okay. Now I want to get rid of the w squared. Okay, largest eigenvalue of w squared. What is the largest eigenvalue of w squared? Yeah, what are the eigenvalues of w squared? So we actually got rid of mu1. Mu1's gone. So what's left is mu2 mu n, but it's actually w squared. So it's going to be mu2 squared, mu3 squared, mu4 squared, this kind of thing. So, and it's actually to the kth power, right? So it's actually to the 2k. So, delta max, maximum of mu2 to the 2k, mu n to the 2k, uh, d minus 1/2 x, d to the minus 1/2 x. So we're gradually nibbling away at this. Okay, we just have one term left. How can I get rid of it? Uh, maximum of these two things. We'll move the d over. D minus 1 x. Yeah, the largest degree will correspond to the minimum. I mean, the largest entry will correspond to the minimum degree in the graph. Uh, sorry. But this could be -1. or close to -1. So when you square it, the smallest one can come back to bite you. Uh, yeah, so that is right. Um, so I guess okay. So okay. Now, this part's a little bit annoying. So, okay, so this thing is at most 1 because it's a probability distribution, so the Euclidean distance is at most 1. So the worst case is actually if all the mass is on one vertex, and then that'll get Euclidean distance 1. But for example, if it was like evenly spread, 1 over n, then you would square it, add it up, you get like 1 over n Euclidean norm. So Euclidean norm of x is at most 1. Okay, so now the theorem was technically stated in terms of this gamma. Okay, so this term here is 1 minus gamma to 2k. Okay, so this is at most the delta over delta, 1 minus gamma to the 2k. Okay, and that is it. So that was doing the Euclidean distance squared between where you are in the stationary distribution. But you take the square root and you get square roots around everything, and 2k becomes 1k. And that's our theorem. Okay. So to recap what happened, um, symmetric matrices actually have extremely transparent structure, right? They're basically diagonal matrices. And the reason we're able to get such a clean bound was because the random walk matrix, while non-symmetric, was similar to a random walk matrix. We do that similarity mapping, and the powers of these symmetric matrices are so well behaved, right? Because it's just like powering a diagonal matrix, right? And then we just looked at the powers, and that's exactly where our bound came from. Okay. Yeah, so if the graph is periodic, you won't converge to the stationary distribution. You'll bounce back and forth. So that means that either mu2 or mu_n must have absolute value equal to 1. And in fact, say a bipartite graph will have mu_n is equal to -1. But there still exists a stationary distribution because 1/2 is a stationary distribution. This won't converge to it. Yeah. So especially if you have like two disconnected components, you could put all the mass here, all the mass here, or any combination. But if the graph is strongly connected in a directed graph, then the distribution is unique. And that's coming from the Perron-Frobenius theorem, which the proof we didn't fully do. It's sort of in the same bin as multiplicative turnoff. But uh, but yeah. So in fact, if the graph is strongly connected, you can show it's unique. So the only exception is when you have disconnect for the undirected graph when you have separate components. Yeah. Good. Any questions?